Welcome to the lecture on Matlab demonstration of Laplace transform. In the main lecture on Laplace transform, we have seen that it is a mathematical tool where a function in time domain which can be represented by ft, this particular function can be transformed into another domain called S domain, which is a complex domain, and this is the particular formula for mathematical formula for this particular transformation. Right now, when it's a time domain signal and we convert it into a frequency domain, then we see that this S has two components. One is sigma, another is omega. This omega is an imaginary part, so it comes with j omega term, and then sigma is the real part. So this is the entire complex plane, or called S plane, right? So we see that the definition of Laplace transform is something like this. Okay, we have a time domain signal, we transform it into frequency domain, or we say S domain. What is the condition of existence? The function must be piecewise continuous and of exponential order. Okay, I have narrated these terms. Then S is a complex variable, right? Fine. Now we take one example of a decaying exponential function. It is represented as ft equal to e to the power at. Okay, now we apply Laplace transform definition like this. So any function ft, when we take a Laplace transform, we write it like this, right? What is the outcome? The outcome becomes capital F, and then the variable will be S variable. Okay, sometimes this particular function is written as e to the power minus at ut. What is ut? Ut is a step function. How does it look like? The step function is a function something like this, where it is 0 till t equal to 0, and after that it takes a magnitude of 1 till t tends to infinity. Okay, so what do you mean by writing this? When t is greater than 0, e to the power minus at ut is actually e to the power at, but it shows that there is no component beforehand, right? So either you write ft equal to e to the power minus at and t greater than equal to 0, or you can write ft equal to e to the power minus at ut, right? Both have the same meaning. Okay, now what happens when we compute the Laplace transform of this particular function? Okay, the formula, if we go back, this was the formula. Whatever be the function ft, we multiply it with this particular exponential term e to the power minus st. We take the integration from 0 to infinity, and that also shows that the time starts from 0 and goes to infinity, right? Till that time we will do the integration. So what is our ft? Our ft is e to the power minus at. We multiply it with e to the power minus st, then we do the integration, and finally it comes out to be like this. Okay, so this is the final value, right? Okay, now I will show you the Matlab demonstration. So we use the function sims, and we define the variables as symbolic variables. So we take the value variable a, we take the variable time t, and then y is another variable which might not be required here, but we will put it like this. Okay, so and we have f equal to exponential of minus a to the power t, minus a into t. Okay, this is what we write, e to the power minus at. Okay, now when we take the Laplace transform, how are we going to do it? By Matlab, right? we write it as this. Okay, fine. So if we run this particular code, we see that this is what it comes. If we go back to the presentation and see it, then also you see the particular things comes like this, right? 1 by s plus a. Okay, fine. Now when we have this one, after that what we can do, we can use this particular Laplace function to find out different Laplace transformation of different functions, right? So just to show you how what happens when it becomes e to the power at, f equal to e to the power at, right? If we run it, we'll see it becomes minus of 1 by a minus s, that means 1 by s minus a. You have seen in the last lecture that when we take the Laplace transform of e to the power at, then it becomes 1 by s minus a. When it is minus at, what happens? It becomes s plus a, 1 by s plus a, right? Okay. Now what we can do here in this particular example is that we can take different functions. Okay, so if we take some function, say t, then what will happen? It is 1 by s square, right? What is this function called? This function is known as unit ramp function, right? Now we'll change the function. Okay, how we change it? We take a different function, say sin x y, okay, and we take a function where y is a function of x in this way, f is a function in this way. Okay, when we take a Laplace transform, we'll see what is happening. You see this is no more one unit ramp function, it is a function 1 by square root of x, and when we do the Laplace transform, we see it comes as root over pi by root over s. Okay, fine. Now we take some other functions. We write symbolic variables as t and s. Okay, then we write some other symbolic functions as symbolic variables as a, which is positive. Okay, and what we do here is we define the function f as a direct delta function. How we will do that? We write it like this: f is a Laplace transform of a Dirac delta function t minus a with variables t, and it will be transformed to s. What does it happen? So Dirac delta function, only when it's a delta function, it is what? It is only 1, the Laplace transform becomes 1. But when it's a t minus a, that means the Dirac delta function is getting delayed by unit a, right? So when we have seen in the lecture that when there is a delay element and we take a Laplace transform, it comes as this shape. So f becomes e to the power minus as. Accordingly, whatever be the function, if we delay it to some other points or by some unit, then whenever we take a Laplace transform, it will come like this. Okay, fine. Now if we do the Heaviside transformation, then what will come? The students are encouraged to go through the particular functions if they are not familiar enough. So, if we change the function f from Dirac delta function to Heaviside, and that to delayed version of that, then see what is coming. It becomes e to the power minus s minus as by s. If we remove this particular value a, then what is happening? It becomes 1 by s. Okay. Okay. The thing is that I would request the students to think about this function and remember that when it is 1 by s, the Laplace transform is 1 by s, it comes from a step input. So, try to coordinate between these two functions and do the Laplace transform. You are encouraged to compute the Laplace transform of these basic functions by hand using the mathematical formula. At the same time, also use Matlab to simulate it. So, there will be a nice understanding of the entire lecture set, and you will be able to visualize how Laplace transform is being computed. Okay, fine. Now, we will see kind of Laplace transform for different functions, okay, like the derivative of a function. How we do that? We will take a function, say sims ft and s, okay. Then we write the differentiation of this function as this. When we use the symbolic variable, we can do the direct differentiation like this. So, it is a differentiation of ft in terms of t, sorry, okay. So, when we take this function's Laplace transform, then we have to write it like this: f equal to Laplace of df t s, okay. So, it is a Laplace transform of derivative of f with respect to time, or the Laplace transform of f dot t. If we do it like this, since we do not know what is going to be the function f, that is why it does not write it as f for a specific function. For any function it is true. How it will come? It will come as f equal to s f s minus f 0, right. So, we have seen in previous lectures as well that when we are doing it like this and we have a particular function, say f t, and actually we work on its derivative f t. If the Laplace transform of f t is f s, then the Laplace transform of this derivative term is s f s minus the initial value of the particular function, right. So, this is the Laplace transform, okay. So, what we have seen just now in the previous example of this Matlab demonstration is that since we do not know what it is going to be the function f t, that is why this particular Laplace transform is written in a generic form, which shows that s will be multiplied with the Laplace transform of small f t with respect to time t, okay. Then what it becomes? It becomes f s. This particular term becomes f s. So, capital F is equal to s f s minus f 0, okay. Fine. So if the Laplace transform directly cannot be found, if the Laplace transform cannot transform the particular function Laplace cannot transform the input, then it returns some unevaluated call or result. So by this way you can see that what it is coming to be. Say the next example will take in a similar line where we will specify the function f of t like this. F of t is 1 by t. Okay. Now what is fs? Fs is what is f? F is the Laplace of the function f, t and s. Okay. You see what it comes. So it is telling that since we don't specify this particular function, it comes as whatever be the Laplace of 1 by t will be the Laplace function. So in this case Laplace cannot transform the input and it returns an unevaluated call. Okay. So return if we want to return the original expression from this particular thing, what we have to do, we have to okay, so we have this f, capital F, right? Now if we want to see what this f is going to be, we have to do one inverse Laplace. Okay. So if we write ft is equal to inverse Laplace of this particular capital F s t. So when we write t comma s, it is a Laplace transform from time domain to s domain. During inverse Laplace, what we write is s comma t. That means from s domain we are now transforming it back to the time domain. Okay. If we do that, then how it will come? See, we were not being able to specify what is the fs, that's why it was writing Laplace 1 by t, but when we do the inverse Laplace, then conveniently it gives back 1 by t. Okay, fine. Now we change the function. Say sine of at, then what is going to be the Laplace transform? Let's see. It should be a by s square plus a square. If you compute it mathematically, then also you can verify it. It becomes a by s square plus s square, right? If the a becomes 1, then what we will get? 1 by s square plus 1. Okay. If sine is converted to cosine, then what we will get? We will get s by s square plus 1, right? See. Okay. So you can see that when you have this particular command Laplace, you have the function being specified, then you can convert or transform the function from its time domain to s domain counterparts. If these functions are not being evaluated by Laplace or not being the function is not being able to be specified, or the command Laplace cannot transform it properly, then what it can do is that it will send back one unevaluated call. Okay. If we want to get back to the original format, then we have to do one inverse Laplace. Okay. So this is how Laplace transform works in Matlab. It is a very like unique software for all kind of control system design. We have gone through the lecture on introduction to control system, where we have seen why control system is important, how it functions. But in order to appreciate the specifics of control system, we have to understand Laplace transform. So we have gone through another lecture on Laplace transform, where we have derived things mathematically. We have gone through the notion of time domain and s domain. We have seen that in s domain there is a real part and imaginary part. So it's a kind of two-dimensional plane. One part is real, another part is imaginary. The thing which was remaining in this particular area is that if we want to do the same thing with MATLAB, then how we are going to do. Okay, so we see that using the command Laplace we can get the Laplace transform of different functions. If we specify the function as our known functions, like exponential functions, e to the power minus at or e to the power at, sin omega t, cos omega t, ramp function, delta function, when we are specifying the function we get the Laplace transform accordingly. When we don't specify the function, as we have seen that we were writing the function as just ft, we have taken the derivative and wanted to take a Laplace transform, then since we don't know the function ft, it will come as a generic symbol. And when the command Laplace cannot be useful for getting the exact Laplace transform, then it will give one unevaluated call, and from that we can get back the original function by taking by using the command iLaplace. Okay, so we hope this particular lecture will be clear to the students and they will be use it is easier for them to use this particular command when they are writing the codes. It will be a suggestion to the students that they, whenever they are doing some Laplace transform for a particular function, first they do it mathematically by hand, compute it properly, and then to get a better insight they simulate it in MATLAB and then check what is going to be the results. Thank you.